Hi, it's Tom again. Last time we had a look at the decoupling capacitor and how it functioned like a band stop filter due to all the parasitics being present. This time we'll have a look at a more of a practical case where we look at the mounting of a filter, in this case a pie-shaped low-pass filter, where you can see the schematic here, and where we're gonna have a look at how to mount this and the importance of grounding such a filter. So here you can see the board, which is aptly called grounding of filters, where we have 4 filters which are the same, but mounted in different ways. So here we can see the entire measurement setup, where we have our board connected to the VNA, which is connected to our laptop, and where we measure the S21 parameter of the filter, and where we will show the S21 parameter for the frequency range going from 1 to 1000 MHz. So let's first have a look at this top filter configuration, where the input and the output of the filter is connected, but the filter has not been grounded at all whatsoever. So let's first have a look at what we expect this filter to do when we haven't grounded it. So here we can see the schematic again, but this time we haven't grounded the decoupling capacitors, thus just surpassing the functionality of these decoupling capacitors. But however, we still have this inductor which should still act as a low-pass filter. So let's have a look at the results where we expect a low-pass functionality. If we do the sweep, however, we see that it does not function as a low-pass filter whatsoever. Why this is the case, we can see when we have a closer inspection of the mounting of the filter. So let's look at the board again. So let's have a closer look at the filter, where we can see that a capacitive coupling is created between the input and the chassis and the output, creating a path of lower impedance with respect to the inductor inside the filter, thus not functioning as a low-pass filter, which we see on the screen. So now let's have a look at the second filter configuration, where it is connected via a long input wire and a long output wire, and it is grounded this time, but also with a longer green wire. So for this filter configuration, we expect a better low-pass functionality due to the fact that this time we actually connected the decoupling capacitors. So let's have a look at the results. So when we do the single sweep from 1 MHz to 1000 MHz, we expect a better low-pass functionality. We do see a bit of a better functionality, but nearly not good enough with what we expected. Why is this the case? Well, let's have a look at the board again. Apart from actually connecting the decoupling capacitors this time, this larger return path of the grounding also introduced mutual coupling of the input and the output, bypassing the filter functionality. We can see this in the results at around 9 MHz, where the inductance takes over. So now for our third configuration, we take out this long grounding wire and replace it for a short mounting, where we expect this mutual inductance of the input and the output to be lowered, thus improving the low-pass functionality of the filter. So let's have a look at the results again. And indeed, this time we see a much better performance of the low-pass filter due to the proper mounting of the filter and the proper grounding. And for our fourth and final configuration, we have a short input path and a short output path. We have a shielding of the input from the output. We have a properly connected ground, and we have the entire track surrounded by a ground plane, minimizing possible loops. So let's have a look at the low-pass functionality of this filter. And when we do a sweep of this properly mounted filter, we see the best possible low-pass functionality that we can achieve with this filter. So when we compare the results of these 4 configurations, we can see the huge impact mounting the filter has on the functionality of the filter itself, even for such a simple low-pass filter.